Welcome to Spot Podcast, the voice of scientists, where groundbreaking research meets your ears. We bring you the world's top-cited research articles in an engaging podcast format, making cutting-edge science accessible anytime, anywhere. Stay informed, stay inspired. This is the Spot Podcast, the voice of scientists.
Hey everyone, ready for another deep dive? Today we're looking into something that's pretty relevant to the future of, well, transportation, I guess you could say.
Definitely, yeah. Electric vehicle battery recycling.
It's a hot topic these days.
Absolutely. A lot of buzz around it.
For sure.
Right.
We've got a whole bunch of research for this one. But the core piece is a scientific paper called Recycling Lithium-ion Batteries from Electric Vehicles.
Oh, very interesting.
Yeah. Plus, we've got a few other reports and articles just to give us a bit more context. Now, think about this for a second. We're in the middle of this electric vehicle revolution, right? But what happens to all those powerful batteries when they're done?
Yeah, it's a big question.
Mhm.
And I think it's a question that the industry is really grappling with right now. I mean, these batteries, they present some real challenges environmentally, economically, but they also present some incredible opportunities too.
Yeah, for sure. So that's what we're going to unpack in this deep dive. We're going to break down all the science, the strategies behind recycling these lithium-ion batteries, and we'll talk about the dangers, the cutting-edge tech coming into play. And of course, we'll leave you with some food for thought about the future of this whole industry.
Yeah. You know what I find fascinating is that recycling isn't always the first priority. Have you ever heard of the waste management hierarchy?
I'm not sure I have. Fill me in.
Well, it basically prioritizes reuse over recycling. So it's all about optimizing material use and life cycle impact.
No, so it's like giving these batteries a second life before they head to the recycling plant.
Exactly. And there's actually a growing market for these used EV batteries, things like energy storage. You might even have a second life battery powering your home one day, storing energy from your solar panels or something like that.
Oh, yeah. I have actually read about companies using these old EV batteries to build those giant backup power systems for the electrical grid.
Exactly. Those are perfect examples. And one of the ways we measure how effective this second life is through something called ESOI energy, stored over energy invested.
EOI. Huh. What is that all about?
Well, it basically compares the energy that's needed to make the battery in the first place with how much energy it can store over its lifespan. You can see how giving a battery a second life, like in a home energy storage system, it really boosts that ESOI score.
Right. It becomes much more sustainable than just recycling it right away.
Exactly.
That makes a lot of sense. Extending the life of these batteries is good for the planet and good for our wallets. But even with a second life, they eventually all need to be recycled, right?
Absolutely. And that's where things get a little bit tricky. We start to run into some challenges.
Yeah, I've heard it's not exactly a do-it-yourself project. What are the risks involved?
Well, you've got the potential for electrocution, of course, short-circuiting, which can cause rapid discharge and overheating. And then there's something called thermal runaway.
Thermal runaway. That sounds a bit scary.
It is. It's essentially a chain reaction where the battery heats up uncontrollably. And that can lead to fires or even explosions. On top of that, you've got the release of toxic gases, things like hydrogen fluoride or HF.
Yeah, that's not something you want to mess with.
No, not at all. It's highly corrosive. And if you inhale it, that's really dangerous. So safety is absolutely paramount when you're dealing with these batteries. But beyond the safety issues, there's also just the challenge of complexity.
You mean like just the nuts and bolts of taking these battery packs apart?
Yeah. Each EV manufacturer, they've got their own battery designs, their own chemistries. The paper mentions 3 distinct designs, actually. There's one from Tesla that uses cylindrical cells, another from BMW with prismatic cells, and then a third from Nissan with pouch cells.
Huh. So each one poses its own unique set of challenges, I guess.
Exactly, like the Tesla battery. They use an epoxy resin to bond those cylindrical cells together. And that stuff is really tough to remove and recycle. Then you've got the BMW battery with those large prismatic cells. They're under a lot of pressure, so if they've degassed, it can be really dangerous to open them. And then the Nissan battery, that one has a high manganese content, which actually poses a challenge for a specific type of recycling called pyrometallurgical recycling. That's because manganese is a relatively cheap metal.
So it's almost like a logistical nightmare to try and recycle these things on a large scale with all these variations.
Yeah, you could say that. And that's a big reason why the industry is really excited about the potential of automation and battery recycling.
Robots to the rescue. Tell me more.
Yeah, there's a ton of potential here. Robotic disassembly could drastically improve safety, cut down costs, and it could even increase the value of the materials we recover because it allows for more precise separation.
That sounds pretty futuristic. But can robots really handle that kind of intricate work? Especially with all the variations in design we just talked about? How would they adapt to all that?
That's the big question, right? Like, it's one of the biggest hurdles robots face. They usually excel in these structured environments with predictable tasks. Battery recycling is anything but predictable.
So how do we bridge that gap then?
Well, researchers are making some incredible strides in areas like computer vision, artificial intelligence, and robotics that's specifically designed to tackle these complex disassembly problems.
So they're teaching robots to think like recyclers.
Exactly.
Wow.
They're making them more adaptable, more intelligent. Some are working on algorithms that allow robots to recognize different battery types based on visual cues like size, shape, color, even labels or QR codes.
So they can see what they're working with.
That's right. Others are exploring tactile and force sensing capabilities. So the robots can actually feel what they're doing and handle those delicate tasks without causing any damage or triggering any hazards.
That's amazing. It's like a whole new level of robotic dexterity.
It is. We're not quite there yet, but the progress is really promising.
This is fascinating stuff. But let's not forget about what happens after the batteries are safely taken apart. How do we actually recycle the materials inside?
Right. Well, it's not as simple as just tossing them in the recycling bin. The process itself is actually quite intricate. It all starts with stabilization.
Stabilization. Why is that so important?
Remember all those dangers we talked about earlier? Well, before we can even think about processing these batteries, we need to make sure they're stable. They can't pose any hazards.
Right. Makes sense.
Yeah.
So how do they do that?
There are a few methods. One involves completely discharging the batteries, either by immersing them in a special salt solution, it's kind of like a spa treatment for batteries, or by connecting them to a circuit that drains their energy.
Wait, they dunk batteries in salt water.
They have used seawater in the past, but it's not ideal. It can cause too much corrosion and contamination. Researchers are looking into more controlled solutions now, using specific salts to get the job done.
Interesting. And what about that other method, draining the battery's energy?
It's basically like plugging the battery into a device that uses up all its juice. The good thing about this is that you might be able to reclaim some of that electricity, offsetting some of the recycling costs.
Oh, I like that. Turning waste into a resource.
Right. Now, these discharge methods work, but the industry actually prefers something called in-process stabilization.
In-process stabilization. What's that?
It's a more streamlined approach. The batteries are shredded or crushed under a blanket of inert gas, like nitrogen or carbon dioxide. This prevents any reactions with oxygen that could spark a fire or an explosion.
So it's like disassembling and stabilizing all in one go.
Exactly.
Right.
There are a few companies that use this method, like Recapol in France, Accuser in Finland, Duesenfeld in Germany, and Retreat in the US and Canada.
And each company has its own unique twist on the process, I'm guessing.
You got it.
Yeah.
Like Retrieve, they use a water spray during that opening step to help control temperatures and prevent thermal runaway.
Wow. So once the batteries are stabilized, what happens next?
That's when we get into the real nitty-gritty. We dive into all the different methods they use to extract those valuable materials.
Okay, let's dive in. What are these different recycling techniques all about?
So the first one we'll talk about is called pyrometallurgical recovery. It's a high-temperature process that essentially smelts the batteries to recover those valuable metals.
Smelting. That sounds pretty intense.
Yeah. Picture melting down batteries in a giant furnace. The high temperatures break down all the components and separate the metal from everything else.
So what comes out the other end?
Well, you end up with a few things. You get a metal alloy that contains cobalt, copper, iron, and nickel.
Those are valuable,
Yeah.
especially cobalt.
Exactly. And then you have slag. It's a byproduct that usually contains aluminum, manganese, and lithium. And then, of course, there are the gases that are released during the process.
And what do they do with all that stuff?
Well, the metal alloy can be further refined to separate out the individual metals. The slag can actually be used in other industries like cement production.
Oh, wow. So it's not just about recovering the metals. It's about minimizing waste and finding new uses for those byproducts, too.
Exactly. It's all part of sustainable recycling. But pyrometallurgy does have its downsides.
Like what?
Well, for one, it's a very energy-intensive process.
Yeah.
Those high temperatures require a lot of energy to maintain.
Right. So there's an environmental cost involved.
There is, and you also have limited material recovery. Pyrometallurgy mainly focuses on those high-value metals like cobalt and nickel.
What about the other materials, like the lithium and the electrolytes?
Yeah, those often get lost during the process. Plus, there's the concern about toxic gas production, which needs to be carefully managed to prevent environmental harm.
So while pyrometallurgy is a commercially established method, it's not perfect.
No, it's not, and that's why there's so much research going on into other methods that might be more efficient and more sustainable.
Okay, so let's talk about those alternatives.
Yeah.
What are some of the other options out there?
Another common method is called physical materials separation.
Okay, so what's the basic idea behind that one?
Well, instead of using heat, this method relies on the physical properties of the battery components to separate them.
Huh, interesting. So how does that work in practice?
After the batteries are shredded, they go through a series of steps. You've got things like sieves, filters, magnets, and even a technique called froth flotation.
Froth flotation. That sounds kind of fun.
It's like a bubble bath for battery components. The materials that repel water, they cling to air bubbles and float to the top, separating themselves from the rest.
That's pretty clever. So what's the main goal of this physical separation process?
It's all about creating something called black mass. It's basically a concentrated mix of those electrode coatings which contain the valuable metals we're after.
Ah, so it's like a pre-processing step to concentrate the good stuff before moving on to further extraction.
You got it. Physical separation is great at creating this black mass, but it also has its own challenges.
What kind of challenges?
One of the biggest hurdles is removing the polymeric binders that hold the electrode materials together.
Binders. What are those exactly?
They're like the glue that keeps the active materials and the electrodes in place. The problem is some of them can be really difficult to remove. PVDF, for example, polyvinylidene fluoride. It's a common binder that's a real pain for recyclers. It's a tough polymer, great for battery performance, but not so great for recycling. So researchers are looking for alternatives that are easier to break down.
So removing those binders is critical for getting those metals out of the black mass.
Exactly. And researchers are exploring all sorts of methods for that, things like solvents, thermal treatments, and even ultrasonic techniques.
Wow. It's amazing how much science goes into all of this. So physical materials separation is a key step, but it's not the end of the line. What happens to that black mass after it's created?
That's where hydrometallurgical metals reclamation comes in. This method uses aqueous solutions, basically liquids, to leach or extract the metals from the cathode material.
Leaching. Okay, I need a little more explanation on that one.
Think of it like a sophisticated sorting machine that uses chemical reactions to pick out the valuable metals from everything else.
Okay, that makes sense.
The most commonly used reagents are sulfuric acid and hydrogen peroxide.
So it's all about finding the right chemical cocktail to pull out those desired metals.
You got it. And while hydrometallurgy is effective at recovering metals like cobalt, nickel, manganese, and lithium, it's not without its complexities.
No kind of complexities?
Well, modern cathodes often contain a mixture of different metals.
Mm.
The paper mentions NMC cathodes, for example. They contain nickel, manganese, and cobalt.
Right, like we talked about with the different battery designs.
Exactly. Separating these metals from each other can be tricky, often requiring additional steps, like solvent extraction or carefully controlled precipitation reactions.
Like a multi-step purification process to isolate each metal.
That's a great way to put it. And then there's the issue of the sheer volume of solvents needed.
What do you mean?
Hydrometallurgy typically uses a lot of solvents, which can be expensive,
Yeah.
and they can pose environmental concerns if they're not handled properly.
Right, those chemical baths could become a problem in themselves.
Exactly. Plus, there's always the risk of cross-contamination.
Cross-contamination, how does that happen?
If the metals aren't completely separated during the leaching process, you can end up with impurities. That affects the quality of the recovered materials.
So it's a delicate balancing act to optimize the extraction and minimize the risks.
Absolutely. Even with those challenges, though, hydrometallurgy remains a key player in battery recycling.
So we've covered pyrometallurgy, physical separation, and hydrometallurgy. Are there any other methods we should know about?
There's one more that's really interesting. It's called direct recycling.
Direct recycling. What makes that one stand out?
Instead of breaking down the cathode material into its individual metal components, direct recycling aims to recover and recondition either the whole cathode or the anode material, and then it's reused directly in a brand new battery.
So you're basically giving the cathode or anode a second life without having to extract and purify the individual metals. That's pretty cool.
It is, and it has the potential to be much more cost-effective and energy efficient than the other methods, especially for certain types of cathodes.
Which ones, for example?
The paper highlights cathodes like LMO, lithium manganese oxide, and LFP, lithium iron phosphate, as being well-suited for direct recycling.
Why those specifically?
Because the manufacturing costs for those cathodes are relatively high. So being able to reuse the material directly offers a big economic advantage.
Makes sense. It's all about maximizing value and minimizing waste.
Exactly. And the paper even mentions successful examples of reusing mechanically separated graphite anodes.
Oh, so it's not just limited to cathodes. It can work for anodes too.
That's right. But despite its potential, direct recycling does face some obstacles to wider adoption.
What are some of those obstacles?
Well, for one, it's very sensitive to the health of the battery. If the battery has degraded significantly, the recovered material might not be good enough for reuse.
Ah, so it's not a universal solution. You need batteries that are in relatively good condition.
Right. And then there's the issue of dealing with a mix of different battery types.
You mean all those variations in battery chemistry we talked about earlier?
Yeah.
Tesla, BMW, Nissan, they all use different formulations?
Exactly. Direct recycling works best when you have a consistent feedstock of batteries with the same chemistry. But when you have a mix of different types, it becomes much harder to develop a tailored recycling process.
It's like trying to bake a cake with a random assortment of ingredients. You need the right recipe to get the desired result.
Exactly. And each cathode material has its own specific formulation, that precise mix of elements that gives it its unique properties.
Right.
So for direct recycling to be successful, the recovered material needs to match those exact requirements. Otherwise, the performance of the new battery could be compromised.
That makes sense. So while direct recycling has huge potential, there are still some kinks to work out before it becomes mainstream.
Definitely.
This is also fascinating. It sounds like there's a ton of research and development going on in this field.
There's a lot of exciting work being done, and there's one final method worth mentioning, although it's still in its early stages. It's called biological metals reclamation.
Biological. You mean using living organisms to recycle batteries?
You got
Wow, that's next level stuff. Tell me more.
Essentially, it involves harnessing the power of bacteria to extract metals from those cathode materials.
So instead of harsh chemicals or extreme heat, you're using tiny microbes to do the work.
That's the idea. And research suggests that certain types of bacteria are naturally drawn to specific metals like cobalt and nickel, which are difficult to separate using traditional methods.
So it's like nature's own recycling crew.
Exactly. And while bioleaching is still in its early stages compared to the other methods, it has the potential to be a really valuable tool in the battery recycler's toolbox, especially for separating those tricky metals.
It's incredible to think about all the different approaches being explored. From high-tech robotics to harnessing the power of nature, it seems like every option is on the table.
Absolutely. The challenges are real, but so are the opportunities, and the work being done is really exciting.
This has been an eye-opening discussion. But before we wrap up this part of our deep dive, I'm curious to hear your thoughts on the big picture. What are some of the key takeaways from everything we've discussed so far?
I think it's pretty clear that recycling lithium-ion batteries is far more complex than it might seem at first glance. It's not just a matter of melting down some batteries, it's a multi-stage process, each with its own intricacies and challenges. And we're only just starting to explore the potential of things like robotics and bioleaching.
It really highlights the importance of innovation in this field, especially as the electric vehicle market continues to grow.
Absolutely. As we move toward a future with more and more electric vehicles on the road, establishing efficient and responsible recycling systems for these batteries is going to be essential.
So it's not just about the technology itself. It's about creating a sustainable ecosystem for the entire life cycle of these batteries.
Exactly. We need to consider everything, from the design of the batteries themselves to the collection, the transportation, and the processing of those end-of-life batteries. And it's going to take collaboration across different industries, from automakers to recycling facilities, to make it all happen.
It's a multifaceted challenge that requires a truly collaborative approach.
You got it. And it's a challenge we need to face head-on if we want to ensure a sustainable future for electric transportation.
This has been a fantastic start to our deep dive, and I'm excited to hear more about the challenges and opportunities ahead for this crucial industry.
Yeah, and that brings us to, I guess, the heart of the matter, the challenges and the opportunities that are shaping this industry.
Right. So where do we go from here? What are the biggest roadblocks standing in the way of widespread sustainable battery recycling?
Well, I'd say one of the most pressing issues is just the sheer scale of the challenge.
You mean the number of EV batteries that'll eventually need to be recycled? That's a bit daunting, isn't it?
It is, yeah.
Yeah.
As electric vehicles become more and more popular, we're going to see a huge influx of batteries that need recycling. And frankly, our current infrastructure just isn't ready to handle that kind of volume.
So it's a race against time to scale up these recycling processes.
Exactly. And it's not just about building bigger recycling plants. It's about making the processes themselves more efficient, more cost-effective.
Right. If recycling is too expensive or too complex, there's a risk that those valuable materials will end up in landfills.
Exactly. That's the danger. To avoid that, we need to prioritize innovation.
What kind of innovation are we talking about specifically?
Well, the paper highlights several areas for improvement. One is sorting technologies.
You mean better ways to categorize those batteries based on their chemistry and condition?
Exactly. If we can accurately and efficiently sort batteries up front, it streamlines the whole recycling process down the line.
Makes sense.
And that leads to the next area, electrode separation.
Okay. Why is electrode separation so important?
Remember those challenges we talked about earlier, like removing binders and separating the different metals?
Yeah, those were definitely some of the trickier aspects.
Well, if we can find ways to cleanly and efficiently separate the electrodes before those later stages, it could really simplify and improve the whole process.
Right, so it's all about optimizing each stage of that recycling journey.
Exactly. Another key area is process flexibility.
Flexibility, what does that mean in this context?
Well, as we've discussed, battery technology is always evolving. New chemistries are popping up all the time.
That's a good thing, right?
Absolutely. But our recycling processes need to be adaptable. They need to be able to handle these new formulations as they emerge. We can't be stuck with technologies that only work for yesterday's batteries.
So we need to future-proof our recycling capabilities.
Exactly. And that brings us to what I think is maybe the most fundamental area: design for recycling.
Design for recycling. So what exactly does that entail?
It's about considering recyclability from the very beginning, during the design phase of the battery itself.
So instead of being an afterthought, recycling is built into the battery's DNA.
Exactly. If manufacturers design batteries with recycling in mind, the whole process becomes much more efficient and effective.
Can you give me an example of how that would work in practice?
Sure. One example is in the choice of materials. If manufacturers choose binders and adhesives that are easier to remove or break down, it would greatly simplify the separation process.
Right, we talked about how those binders can be a real headache.
Exactly. Another aspect is battery construction.
Okay. How does the construction of the battery affect recyclability?
Think about how those battery packs are assembled. If they're designed in a way that allows for easy disassembly and separation of components, it would be a huge help for recyclers.
So it's about designing batteries that are inherently easier to take apart and recycle.
Exactly. And this is where collaboration between automakers and recycling facilities is crucial. They need to work together to develop standardized designs that optimize both battery performance and recyclability.
It's a win-win situation.
Exactly. And that's where initiatives like the Faraday Institution's ReLib project, the U.S. Resell project, the work being done at CSIRO in Australia, and various European Union projects are playing such a vital role.
It's great to hear about all these different groups working on this problem.
It is. These projects aren't just focused on developing new recycling technologies. They're also establishing best practices and promoting collaboration across the industry.
It's about building a community around this issue.
Absolutely. And as these efforts gain traction, I think we can expect to see some real progress in the coming years.
Okay, so we've talked about the challenges, the areas for improvement, and the exciting R&D that's happening. But let's shift gears and talk about the opportunities. What's the upside of cracking this battery recycling puzzle?
Well, from an environmental perspective, it's all about reducing our reliance on mining for virgin materials.
Right. Mining operations can have a huge environmental impact.
Yeah.
Especially when it comes to things like cobalt.
Exactly. By effectively recycling those materials from end-of-life batteries, we can lessen the need for new mining, which in turn reduces the strain on the environment.
It's about creating a more circular economy for these resources.
Precisely. And it's not just environmental benefits, there are also economic opportunities to consider.
Oh, like what?
Well, we've already established that these batteries are packed with valuable metals like cobalt, nickel, lithium, manganese.
And the demand for those metals is only going to increase as the EV market grows.
Exactly. By establishing these efficient recycling systems, we can create a domestic source of these critical materials, reducing our reliance on imports and potentially creating new jobs and new economic opportunities.
So it's about turning waste into a valuable commodity.
Exactly. And it's not just about recovering those raw materials either. There's also the potential to repurpose and reuse entire battery components, further maximizing their value and reducing waste.
So there are multiple layers of opportunity here.
Absolutely. And as the battery recycling industry matures, I think we'll see even more innovative and creative solutions come to light.
It sounds like there's a lot to be excited about.
Yeah.
But before we move on, there's one more thing I want to ask you about. We've talked a lot about manufacturers and recyclers, but what about the everyday EV driver? What role do they play in all of this?
That's a great question. It really highlights the importance of awareness and responsible consumer choices.
So it goes beyond just driving an electric car. It's about thinking about the bigger picture.
Exactly. For starters, consumers need to be aware of the end-of-life options for their EV batteries.
I imagine most people don't even think about what happens to their battery once they're done with it.
You're right. It's not usually top of mind. That's why it's so important to research and understand the recycling or disposal options that are available. Some automakers have take-back programs. Others partner with third-party recycling facilities.
So you really need to do your homework and choose a vehicle from a manufacturer that has a responsible plan for those end-of-life batteries.
Exactly. And there are also things consumers can do to extend the life of their batteries, which delays the need for recycling.
Oh, interesting. Like what?
Simple things like avoiding extreme temperatures, which can degrade battery performance over time, and being mindful of your charging habits. Don't consistently overcharge or completely drain the battery.
So it's about treating your battery with respect.
Exactly. And as consumer awareness grows, it creates a demand for more sustainable battery technologies and recycling practices. It puts pressure on the industry to do better.
So consumers have a voice in this.
They do. And as the EV revolution picks up speed, that voice is going to become even more influential.
This has been really insightful. But before we move on, there's one more thing I wanted to ask about. The paper mentions the lead-acid battery industry as a kind of success story in the world of battery recycling. What can we learn from their experience?
That's a great point. The lead-acid battery industry has achieved incredibly high recycling rates. Over 99% of lead-acid batteries are recycled in many countries.
99%. Wow. That's amazing. What's their secret?
Well, a few things have contributed to their success. For one thing, lead-acid batteries are much simpler in their construction and their chemistry, which makes them easier to recycle.
Right. We talked about how those lithium-ion batteries with their multiple metals and complex designs are much more challenging.
Exactly. Another factor is standardization. The lead-acid battery industry has adopted these standardized designs, which has made the recycling process much more efficient.
So there's less variation to deal with.
Exactly. And maybe most importantly, there's a strong economic incentive to recycle lead-acid batteries. Lead itself is a valuable material.
So the value of the material drives the recycling market.
Exactly. The lead-acid battery industry provides a really good model for lithium-ion battery recycling.
It does. But lead-acid batteries are so much simpler than lithium-ion batteries. Can we really expect that same level of success with such a complex technology?
That's the question, isn't it? While we might not be able to replicate their success perfectly, I think there are valuable lessons to be learned, especially in those areas of design standardization and creating those economic incentives for recycling.
It's about making recycling the most logical and profitable choice.
Exactly. And as we move forward, it'll be fascinating to see how the lithium-ion battery industry adapts and evolves.
This deep dive has been incredible. I'm ready to hear what the future holds for this industry. All right, so let's talk about the future. What does the road ahead look like for this industry?
Well, you know, I think about a future where battery recycling goes from being this necessary chore to a thriving part of the circular economy. It's not just about dealing with waste. It's about unlocking value, creating a sustainable future.
So from a challenge to a genuine opportunity.
Exactly. And I think those innovative technologies that we talked about earlier, those are going to be the key drivers of that transformation. You know, robotics, artificial intelligence, bioleaching. The possibilities are pretty exciting.
Yeah, it really is mind-boggling to think about what we could achieve.
Imagine robots intelligently disassembling batteries, sorting and separating components with incredible precision. It would be a revolution in efficiency and sustainability.
Like watching a perfectly choreographed dance of high-tech recycling.
Exactly. And, you know, as these technologies mature, they could completely change the economics of battery recycling, make it much more cost-effective and profitable.
Right, so it's not just about doing the right thing for the environment. It's about making sustainability and economic viability work together.
Exactly. Yeah, I also see a future where bioleaching plays a much bigger role.
It still feels a little bit like science fiction to me.
Yeah.
Using bacteria to extract metals. It's amazing.
It is, yeah. And as research in this area progresses, we could see bioleaching becoming a go-to solution for separating those tricky metals like cobalt and nickel.
It's like nature is lending a hand to solve our technological challenges.
Right. And this focus on innovation is going to be essential for addressing that challenge of scale that we talked about.
Right, the huge influx of batteries that are coming.
Exactly. We need recycling solutions that are efficient, sustainable, but also highly scalable.
So we need to think big.
Yeah. And another major trend I see is designing batteries with recycling in mind right from the start.
That design for recycling idea.
Exactly. Yeah, it's a game changer. And I think it's going to become even more important as the industry matures.
So recycling becomes a core part of the battery's design.
Exactly. It requires a shift in thinking, though, from both manufacturers and consumers.
Shared responsibility.
Right. As this mindset takes hold, I see a future where batteries are designed for easy disassembly, components that can be easily separated and recycled.
Creating a circular symphony of materials, nothing goes to waste.
That's a great way to put it.
Yeah.
And this brings us to what might be the most exciting prospect of all, the emergence of closed-loop recycling systems.
Closed loop. What does that mean?
It means creating a system where the materials that are recovered from those end-of-life batteries are then used to create brand new batteries. You eliminate the need for virgin materials altogether.
So it's a perpetual battery cycle.
Exactly. Now, we're not there yet. But I believe closed-loop recycling is the ultimate goal. It's the holy grail of battery sustainability.
It's a beautiful vision, a future where batteries power our world without depleting our resources.
And I think it's achievable if we keep pushing the boundaries of innovation and embrace that circular mindset.
This has been a fantastic deep dive. So many fascinating insights.
It's a really complex topic, but there's so much potential.
It's something we should all be thinking about. The choices we make today will have a big impact on the future of this industry and the planet.
For sure.
So as we wrap up our deep dive, what's one final thought you want to leave our listeners with? Something to ponder.
How about this? If scientists could develop a universal battery recycling process, one that could handle any battery chemistry, any design, any state of degradation, what would that look like?
That's a great question. It's a challenge to all the brilliant minds out there.
Yeah, it's a call to action to create a future where battery recycling is seamless, efficient, and truly sustainable.
Well said. And on that note, I think we'll wrap up this electrifying journey into the world of electric vehicle battery recycling. Thanks for joining us.
It was a pleasure. Until next time, keep those brain cells charged up.
Stay curious, keep exploring, and join us next time for more groundbreaking research brought straight to your ears. Don't forget to subscribe and share, because science is meant to be heard.